other compounds are being many other compounds are being released into the atmosphere. And so those things are longer lived. And so when you look at carbon monoxide, for example, it tends to be smeared out around the globe. And so bringing the information back to sources, where exactly is the human activity happening? So, a lot of people, when they see this map, they ask, well, why don't we have one over South America? Why don't we have one over Africa? And it really comes down to funding and abilities. And so there's much interest in expanding this view. But for now, we've been successful in getting the funding to do GEMS, which is already launched, Tempo, which has launched a couple of years later, and Sentinel-4, which really isn't even on orbit yet. And so for many places across Latin America and where the Americas Working Group is focused, it's really low Earth orbit, tropomi, things like that you're still trying to use. But I would still argue that the satellites are only one part of the picture, of course. And so I want to provide a little philosophy on the beginning of this talk. And so it was in the late, maybe 2007, 2008, that the talk of these satellites, these geostationary satellites, really picked up. And there was a lot of talk about how good they needed to be. And I had lots of questions about what really are these satellites going to do? How are we going to use them? And this idea of the integrated observing strategy that we need began to take form. And so this is the way we describe it today. But we have to bridge between satellite and ground. And so throughout this talk, I'll try to give some examples of that bridging that I'm talking about, because each of these perspectives is very different in what it can provide, but also very fundamental to the picture that we need of the atmosphere. And so I'll mention the satellite first. And from the NASA perspective, the satellite provides that broad view. We can see the landscape as it exists and what's happening across that landscape. But we can only do it for a few things. There's the NO2. I'll mention formaldehyde, which I think is quite important for us to focus on as another important measurement. We can do aerosol optical depth, carbon monoxide, but we quickly run out of things that we can measure from space. And so it's not nearly comprehensive enough to describe things. We also have the problem of geostationary can give daytime coverage, but low Earth orbit is limited in the frequency once per day. The vertical resolution is very limited. We make judgments on vertical profiles, but we really don't know. The retrieval process determines a lot of that. And so is quite an imperfect view that we get from space, but very valuable. And the same is true on the ground. We have air quality monitoring and research sites. There we have continuity. We have the value of things being measured throughout the daily cycle and in great detail. But what happens on the ground is not independent of what happens above. And so even on the ground, you're limited in what you know. You're also spaced out, and you're only measuring in discrete places. And so there's lots of uncovered ground when you're making ground measurements. And so we can see how space and ground are complementary, but how do they really connect? And that's an important question. And the way we can try to answer that is with aircraft. If we can do soundings of the atmosphere, if we can fly above ground and near the ground, and from the aircraft measure many more constituents. From there we can measure more than 100 different things from the NASA aircraft. We can, at least for a short period of time, paint a very detailed picture of the atmosphere and what it looks like. And all of that information from all three of these observational perspectives, the real goal is to develop better models that can both forecast and help us strategize how to both improve air quality and climate. And so in terms of human emissions, the short-term impact is poor air that we breathe. The long-term impact is the accumulation of greenhouse gases and climate change. And I like to remind folks that NO2 vision that I showed on the earlier slide here, if we make changes in our emissions or our policies can change the trajectory of what we're doing, NO2 is the first place you'll see that from space. You'll see an immediate change. We saw that during COVID. COVID was a great example of how changes in our activities show up very quickly in these satellite images. But those short-term changes have very long-term value. And so I want to emphasize that NO2 vision from space actually carries a lot of use. But the models are the place that we want to be able to predict well. If we can predict air quality better and better and better, we begin to have more faith that those models can be used to predict what the response will be if we change something in the system. And so it's very hard to convince a regulator to make decisions about vehicle fleet or power generation or industrial processes without some model prediction of what the benefit will be of doing that. And so training models to be better with these observations, space, ground, and airborne is a very important part of what we pursue as scientists. And that combination, as we know, can be quite complex and change from place to place. There are different combinations of meteorology and topography and density of sources that make this science very valuable. I would argue that we've learned enough to understand how is ozone formed, where do particles come from. We know these things, but we don't know the complexity of how different locations respond to that. And that led to one of my very first field campaigns. This started back in 2010. It was called Discover AQ, a very complicated acronym, deriving information on surface conditions, what's happening on the ground, from column observations and vertically resolved observations of air quality. And so here at that time, we had no satellites that could do geostationary, but we did have the low Earth orbiting satellites from NASA. And the idea was to send aircraft around an urban domain with one aircraft being a remote sensing aircraft. And so one aircraft would fly with a LiDAR and a trace gas spectrometer to be able to map the pollution in a way that satellites would, say a Calypso or a Tropomi or a Tempo, but at a much higher resolution. And so what does that satellite type aircraft see? Then we would take a second aircraft, and it was a NASA P3, and we would do these soundings. And so for many years, we would chase pollution plumes, but what we really needed was vertical soundings of the atmosphere. Ozone sondes and weather balloons do a great job, but not for enough things. What if we took a plane and started taking chemical soundings of the atmosphere, hydrocarbons, greenhouse gases, formaldehyde, NO2, ozone, all those things at once? How valuable that could be. And then finally, doing that sampling in a domain where you're flying over ground monitoring sites. So what do we see for ozone at the ground? What do we see above the ground? What do we see for NO2 at the ground? What do we see above the ground? And how does that all tie together? This was a very important first step in trying to sample the atmosphere with that integrated observing strategy in mind. And we laid this out in 4 different places, Maryland, Houston, California, and Colorado. And in each place, you see this red path of spirals. You see the 2 aircraft following this path, mapping like a satellite would, and then doing the soundings. And then you see things on the ground. So you see ground measurements from air quality measurements. You see these things called Pandora spectrometers. I don't have time to go deeply into Pandora spectrometers, but think of that as a ground-based remote sensor that looks at the sun and tries to measure that same column density that a satellite would. How does that behave? And so now we begin to set up an environment where we can ask ourselves, how does the satellite measurement relate to a ground measurement? How does all that go together to influence our ability to model the atmosphere? And one of the early findings that we had was that the boundary layer is not well mixed. We find that when we do these soundings, we find very, very different distributions. Now, this is not a distribution. This is a calculation of ozone production from the surface to a few kilometers above the ground based on those soundings, those chemical soundings that we did. And the importance of this result is to say that when you calculate ozone production based on ground measurements, those ozone production rates can be much greater than what's happening in the overlying boundary layer. And so that ground level ozone production rate doesn't really represent what you can expect in terms of the diurnal changes in ozone. And it has to do with whether you have a deep turbulent boundary layer where you see that above the ground, the ozone production rates are much closer to what you see on the ground, or these stable environments where what you're calculating at the ground level is so different from what's above that you really are not well representing the environment that as the day continues and you begin to have more mixing, what you can really expect to see in ozone changes. This also goes with measurements I've made for many years. And if you've ever been on an aircraft, you find that as you descend in the atmosphere, the highest ozone is often not near the surface, but above, because above ground, as you dilute the nitrogen oxides and the nonlinearity of the chemistry, you can often have much more effective ozone production rates at altitude than you do down at lower altitudes. And so this was an important part of just demonstrating why information above ground can be really crucial to understanding what's going on. This begins to show you very quickly, what does it look like when you do all of these soundings? And so during this first campaign, we collected more than 300 individual profiles in the atmosphere by taking this aircraft and doing these spirals. And here I'm isolating 4 of those days. And so in orange, you're looking at all of the profiles during the month. This was 10 flights. And in black, you're seeing the profiles only for a given day. And so as we would do the profiles, we would visit each site 3 times. And so think of 6 locations on the ground, 18 spirals, 6 in the morning, 6 in the middle of the day, and 6 late in the afternoon. And so what I want you to see here is that we did 4 days in a row, which was very taxing. I had to do a lot of convincing for the science team to do 4 flights in a row and the pilots, but it turned out to be very valuable. And what you're seeing is that between day 1 and day 4, you see formaldehyde on the top, and you see that the formaldehyde is reaching a higher altitude each day. You see this red line is showing you the boundary layer is deepening over time. Next, you see NO2. The interesting thing about NO2 that I want to emphasize is that the NO2 changes, the NO2 is deeper as well, but you also see day-to-day changes in NO2 that don't really look like the formaldehyde at all. I want you to hold on to that idea because it's going to be important for other ideas later. And then finally, ozone at the bottom. You see ozone is also increasing over time. So you start in sort of the 40 ppb range, and by the 4th day, you're up at 80 ppb of ozone. And so one of the questions we had was, when you look at things from space, can they inform you about ozone? It turns out that NO2, while it's fundamental to ozone formation, is not very useful for understanding the ozone change because NO2 is being constantly emitted into the atmosphere, so it's being replenished all the time. Formaldehyde, however, is a photochemical product that's being produced from VOC oxidation kind of alongside the ozone production. And so what was happening over these 4 days, what you're seeing in terms of this deepening of the boundary layer, was the temperature rose quite substantially. So it was colder on day 1 and it was quite hotter on day 4. And this was also in a very biogenically driven area. So the isoprene emissions increased dramatically from day 1 to day 4. So we ended up getting lots more formaldehyde from isoprene, lots more ozone from the chemistry. And this is a result that I've never replicated anywhere else, but it seeded an idea. And so here, what we did was on the previous slide, we integrated over the boundary layer the amount of formaldehyde and the amount of ozone at each individual spiral site over 4 days. And we ended up with this relationship. So this very, very tightly bound ozone amount with formaldehyde amount. And while this was very, very useful, we don't get ozone amounts from space in terms of just the lower 2 kilometers. What we get is the surface ozone. And so we began doing work on, well, if this works well for the ozone Dobson units in the lower atmosphere, can it also relate to the ground? And it actually does. And I'll show something about that later in this talk. And so it became a very useful idea that can we use formaldehyde from space to say something about ozone? The other thing you get from this is that you see changes in ozone, but you also see large changes in the relative amounts of NO2 and formaldehyde. And, something that was posited many years ago is that formaldehyde and NO2 can be used in ratio to tell us whether we should control VOCs or NOx to improve ozone. And I'm challenging that idea. And the reason I'm challenging that idea is because those ratios usually are derived from very long-term averages, like maybe a month of satellite data for formaldehyde and NO2. And here you see them changing in very different ways. You also see here in an example from Houston that you see ozone here is the black trace, and you see ozone is daily going up and down. And in the squares, which is right off of this scale, you see what the formaldehyde to NO2 ratio was from the aircraft. And you see most of the time it's around this ratio of 2. But on the day when the ozone increased from 60 to 120 ppb, all of a sudden you had this strong drop in the formaldehyde to NO2 ratio. And this reminds us that it's not the average formaldehyde to NO2 that's important, because when you have the extreme episodes, the formaldehyde to NO2 shifts quite dramatically. And currently, satellite observations are not really able to address a daily ratio of formaldehyde to NO2. So we have to be very careful in taking these long-term averages and thinking that they give us the content we need to understand what to control or how to affect ozone. So this was also another very early result that began to affect my feelings about how to use this data and how to make progress on the things that we do for air quality. Now I'm going to jump. I don't have time to go through all the details for these campaigns, but I want to walk you through the thought process. And so the next thing we wanted to do was go to a new place. We worked with Korea on a campaign called CHORUS-AQ. And again, the idea is the same. We knew that they would be launching their geostationary satellite, so we wanted to begin working with them so that we would be prepared as a community to work with the GEMS satellite data and understand, Asian air quality, which has different drivers. And so in this case, you see a picture of the DC-8 aircraft wing and the Lotte Tower. This tower is 2 times taller than any other building in the entire city of Seoul. But we did descents over a heavily instrumented research site just in the vicinity of this area. And so we were able to take, again, these soundings of the atmosphere over a large city like Seoul, which was much larger than any of the other cities that we had sampled before. This was in 2016. And I just want to emphasize really quickly, here you see a different kind of sampling. So all of our sounding was done in this area up here of Seoul, Korea. And then we would do that again 3 times a day. So in the morning, middle of the day, afternoon, we would return to Seoul and do this descent over the city. But in between, we would go out over the water or to the east or to the southeast to try to understand what was happening in terms of long-range transport. With China upwind and the nice opportunity to have a body of water, here's the LOC separating us from China, we could go upwind of Seoul and begin to see what the external influences were on Korea. So you can see how we had the NASA DC-8, the NASA King Air that was doing the remote sensing again, so very similar to Discover-AQ. And then we had a Korean aircraft. And so we had Koreans with us on the DC-8. So there was a capacity building component to this campaign. And again, something I could give you a whole seminar on, but I won't, is the special use airspace in Korea. And the emphasis of that is just to remind everybody that doing these types of campaigns in urban areas, in heavy airspace, is in itself its own challenge. Just getting the permission to fly the planes in these places the way we do can be a full-time job. So I want to just remind people that while this data is very valuable, the opportunities to gather the data are very difficult to achieve. But I want to go back to this question of space versus ground. And I think CHORUS-AQ is one of the best examples of this. And so what do we see from space versus the ground? Here in this figure, the red data is median and interquartile range statistics for a 6-week period of the research site in Seoul. So it's the surface measurement. This is what a ground monitoring site would see. And so the surface NO2 is off of this scale. You see very large amounts. You see up to 30 ppb in the morning. You see still in excess of 10 ppb of NO2 in the afternoon. But the trend that you see is one that we see almost everywhere around the world. You see a very high NO2 in the morning. You see a lower NO2 in the afternoon, and it begins to rise again in the late afternoon. And when you hear people talk about this diurnal trend in surface NO2, you often hear them talk about rush hour, when everybody's driving in the morning. But if you look at traffic statistics, it turns out that they actually are quite sustained all day long. And what you're really seeing, a bigger driver of this trend, is actually boundary layer mixing. And so what you're seeing is the dilution of NO2 throughout the day. And this is demonstrated by the blue curve. And the blue curve is the column amount of NO2. In this case, it's seen from a Pandora spectrometer on the ground, but it's the same thing a satellite would see. And here you see that while the NO2 is decreasing by about or a factor of 2, or even a factor of 3, from 30 down to 10, the total amount of NO2 is increasing by a factor of 2, from about 0.7 to 1.6 Dobson units. And what this is telling us is that while the mixing environment is allowing the ground monitors to see less and less pollution, the satellite is telling you that the pollution is accumulating in the atmosphere. And so there's a lot of opportunity for chemistry above ground that needs to be accounted for. And so in the early parts of our work and the work in the community that still goes on, a lot of people struggle to try to make the satellite match the ground. And I would argue that we don't need the satellite to match the ground because these two pieces of information are independently valuable. The measurements on the ground are extremely valuable to think about exposure, and the measurements from space are extremely valuable to think about the accumulation of emissions, right? And so you're getting two valuable pieces of information from models. Do they capture what we breathe at ground level, but do they also capture the total amount of emission into the atmosphere and how it's happening? And so these two curves and how they differ are very valuable. I talked to some modelers in the early parts of Discover IQ and said, what do you think about this difference in what's at the ground and what's in the column? And they told me, they said, it doesn't make sense. The model doesn't do that. And so they did not believe the column measurements. And so the aircraft measurements are very, very important to both corroborate and help people understand why it looks this way. And so now I'll add the aircraft profile. So now you have a satellite type view, a ground view, and an aircraft view. And here you see in the morning in blue, you see that you have, again, very high. The aircraft is also measuring more than 30 ppb of NOx or NO2 down near the surface. And it's measuring down around 10 late in the afternoon. So this progression of what the aircraft sees is matching this red curve. But you also see in the morning that all the NO2 is below 500 meters. And as the day goes on, mixing brings more and more NO2 that's emitted to higher and higher altitudes. And so this aircraft profiling can help you understand how these two curves are both different, but describing the same system. And so can we capture that in the models is an important part of what we do. But I also want to come back to, there are other molecules. And so NO2 looks this way because it's emitted at the surface and has a very short lifetime. For things with longer lifetimes or things that are absorbed at the surface, like CO2, you'll see quite different profiles. But here I highlight again formaldehyde. And so now I repeat, this is the same NO2 you looked at on the previous slide. This is the formaldehyde. And so again, you see that formaldehyde it looks like it's better mixed, but I would say it differently. It's not well mixed. It's simply created through chemistry. And so as the boundary layer gets deeper, as the availability of water vapor and precursors and radicals grow throughout the day, you're oxidizing the emissions of VOCs over a deeper and deeper layer. And so again, you see the NO2 view and the formaldehyde view respond very differently to boundary layer dynamics. The desire for people to conflate the ratio of NO2 to formaldehyde from space gets even more complicated because they're not mixed together in the same way. And so we can see that the nonlinear chemistry of VOCs and NOx are going to lead to different ozone production rates with altitude. And so can we really use a NO2 to formaldehyde ratio from space to talk about ozone production? I'm skeptical. I welcome the community to keep trying to do that, but I think it's more problematic than we have admitted to ourselves as a community. We moved on to Asia in 2023. And so, in 2024. So just 1 year ago, we began to fly flights in Asia. And this was a long undertaking, but this was the first time we could underfly an actual satellite. But again, we had 2 aircraft. And you see colored areas that represent where the remote sensing aircraft flew. And so in this version, we're not following the other aircraft. We're actually mapping the city. So here's Manila, the Philippines. Here's Kaohsiung, the industrial part of Western Taiwan. Here's Seoul again, Seoul, Korea, being mapped. And here's Bangkok, Thailand. And at the same time, we have the DC-8, which is going outside of the city. So it can map over the city, but it can also map the upwind and downwind regions. The DC-8, again, is going up and down constantly. So this idea of soundings of the atmosphere is so crucial to this work. And also connecting. And so I mentioned earlier that if we don't have strong scientific connections in these partner countries, we can't do the work that we do. And so I do want to emphasize collaborators. And so we have the Department of Environment and Natural Resources, the Space Agency of the Philippines, and the academic community. NIER is the EPA of Korea. JISTA is the Space Agency of Thailand. PCD is their EPA. Ministry of Environments, and National Central University. We really want to do these experiments in very close coordination with the people who do the ground monitoring, the people who study the local environment. I, as a scientist, know air quality chemistry pretty well, but I don't know the local details of these locations and what drives them. And so having that local knowledge is very, very important. I would love to go into much more detail on all of these locations that we sampled, but my time is limited. So I will just emphasize a little bit on IGAC-AWG. And here what I'm showing you is what it looks like to sample Bangkok for NO2 on a number of different days at different times of day. And it's the changes you see from image to image that begin to articulate why the satellite geostationary view is so important, because it doesn't look the same every time. It looks different, and those differences matter. And so as a person who does field campaigns, the most important job for me is to find differences. Differences, if we only measure the polluted day, is boring. We need to measure the clean day and the polluted day and the medium day and ask ourselves, do we understand how the meteorology, the sources are behaving? Does it make sense? Can the models replicate that? And so these differences are very fundamental to the work that we want to do with these campaigns. Here I'm giving you, so just very quickly, we're flying north to south in Thailand. The remote sensing, we can only cover so much ground, but with the DC-8, we can go all the way up to the north. And up here, there's a tremendous amount of burning during this time of year, burning of agriculture, burning of forests and things. And we wanted to understand how much those fire influences are localized or down in the city. And so we flew 4 different days during the campaign. And the true value of the campaign, and this is just carbon monoxide, there are many other things I could plot for you, but you can see that the first 2 days look very different than the second 2 days, because the first 2 days had heavy burning. There was a large rain event, precipitation, and a front comes through. And so day 3 especially looks so much cleaner than days 1 and day 2. And day 3, actually, the blue data that's south of 16 North, the data in the city, Bangkok, is more polluted than the north. And so watching these flip-flops in the terrain, watching the changes in the sources, in the stage of data collection, this is what you want to target. You want to capture large changes and then challenge the models and things to replicate those changes. And that's a very important part of the work that we do. The next stage that I want you to know about is that we want to take this work to Mexico City. So we proposed some work. This work would have taken us back to Asia, to Europe, and to North America, but we only got the funding for half of the project. So we're going to stick with North America, and we are going to do this type of sampling in Mexico City. And so this is just a quick example from the proposal. You can see in this map that we've taken the average distribution of NO2. We've shown an area that we could remotely sense. And so this is not just Mexico City, but trying to cover the megalopolis. We're showing where airports exist within the domain so that we can do low approaches where we can get the aircraft close to the ground, like you saw in that first picture that I showed at the beginning of the talk. You see the location of ground-based remote sensors like Aeronet sunphotometers and Pandora spectrometers. You see ground monitoring sites, and I'm sure that this distribution has changed since we did our proposal. And so trying to bring together the local monitoring in Mexico, the research community in Mexico City area, the aircraft that we can bring, we want to address these scientific objectives of improving the connections between satellites and surface networks, using chemically detailed and vertically resolved measurements. We want to evaluate the magnitude and timing of emissions. One thing that we're learning is that many of the models don't really have emissions that match what happens throughout the day, and these diurnal measurements really help with that. We want to investigate and further develop satellite proxies for air quality. What can we say from space that can help us expand on what's at the ground? And how to investigate the diversity of factors controlling air quality across multiple urban areas. The original goal was on different continents, but right now is deployments to Mexico City and locations. So in 2028, we will spend 30 days in Mexico City making measurements that can help us define more completely what the genesis is and outcomes are for Mexico City's air quality under different scenarios and different days. So I'm excited about this opportunity. In terms of tempo, which has been up for 2 years, I want to talk about how we can stitch these views together. And so this is a simplified view of that observing strategy I talked about earlier. How can we exercise this under tempo using Mexico City? And actually, I'm out of order here, so I'm gonna do something different. So I've talked about doing good chemical measurements, instrumenting aircraft to do the chemistry of the atmosphere as well as the remote sensing of the atmosphere for air quality. And I hopefully I've shown you, there are many other examples, but I've shown you that by doing these chemical soundings, we can show you very clearly that boundary layer dynamics are a fundamental aspect of how air quality unfolds from day to day. But does that help us with predictability? And so coming back to this model, what do we need to do if we want to build on this science, if we want to do something more? And I don't have the money to do this, but I am working hard, given our timeline of 2028, to make this happen. If we want predictability of air quality to improve, we can't just look at the chemistry. We have to start looking at the PBL behavior, not only what it does, but how to predict it. And so I've started engaging NASA's planetary boundary layer community. And so one of the questions is, how do we change our strategy here? And so just very quickly, the NASA aircraft for hammock flights. Originally in the proposal, I had, again, a small aircraft flying high and a larger aircraft flying low. And that's to do the chemistry in situ with this aircraft and to use a LiDAR and a spectrometer to measure the air quality with remote sensing. You saw that in the mapping I showed for Thailand. NASA has acquired a very large B777 aircraft. This is an enormous aircraft, almost too big for the science that we want to do. And they said, you can't have the P3, we want you to use this plane. And I became a little concerned because for the intricate flying that we want to do at low altitude, this aircraft is a little too large, and we can hardly even begin to put in situ measurements on it. This aircraft's much better. What I've convinced NASA to let me do instead is to swap these planes. And so now I have a B777 for remote sensing and a P3 for detailed in situ sampling. So picture this P3 flying up and down throughout the Mexico City area, trying to sample what the distribution of chemistry looks like. Aerosols, their composition, properties, a wide range of VOCs and NOx and other things. The 777 with my budget will carry, again, the LiDAR and the spectrometer, a very important tie to the Tempo satellite. But what if we got more things on that plane? They're putting 6 nadir viewing remote sensing ports. What if we had a wind LiDAR, a water vapor LiDAR, an infrared sounder, a soil moisture measurement? Now we're starting to measure the kinds of things that will not just inform chemistry, but will measure those variables that determine the boundary layer. I think this takes our community further. I think it becomes more cross-disciplinary. It connects the IGAC community to the meteorology community. This is an area that I think is wide open to our community, and Mexico City is one of the first places I would like to try it. I'm sorry to say that the environment in the U.S. is really bad politically, but it doesn't stop me from dreaming and from pushing these ideas. And so I'll be working very hard over the next few years to try to expand. We have the money and we have the funding to do the air quality work. What I hope I can expand this into is to do the meteorology work as well. And so connecting in that way will be important. I know I'm talking at a very high level to a lot of things here, but this to me is less of a seminar and more of reaching to this community and their thoughts on this. I want to finish by talking about the Tempo satellite, though. In my postdoc, I talked in the early parts of this talk about, can we use formaldehyde to inform ozone near the surface? And so I showed that in a very early campaign that the integrated ozone in the lower atmosphere and the integrated formaldehyde from aircraft matched really, really well. But they also matched reasonably for surface ozone. And so we were really kind of shocked to find that these are Pandora spectrometer measurements in the New England, New York area. And these are tempo measurements. This is actually space. And so surface ozone measured on the ground is correlating with a space-based formaldehyde reasonably enough to say that at least in the average, we can say where we think high ozone is happening. Now, this isn't good enough for a model. This isn't good enough for a forecast of ozone, But I would argue that when you have limited locations on the ground that you can monitor, having a satellite formaldehyde product that matches this well can point us to optimization of ground networks. When you have limited funding, where do you measure on the ground? Can we find through formaldehyde the hot spots of air quality that maybe are unmonitored or need more dense monitoring? This is an area that our current research is going to go. And that tempo formaldehyde performs this well is quite exciting for us. And so this is the direction we're going to go. What my postdoc shows here very quickly is that, here you have New York City, right? And on day one, the ground monitors show very high ozone. And that is the day that you have higher formaldehyde. And then on day two, you see that the formaldehyde begins to extend further to the north. It's much cleaner on day one than day two. And you see the ozone responding to that. And then down here in area 3, you again see higher ozone when the formaldehyde is more intense. Oops. And so this idea of, can we use the distribution of formaldehyde from space to talk about how ozone's behaving? And believe it or not, secondary aerosol formation looks like it's also mapping to this metric. And so we're just starting to look at PM 2.5, but PM 2.5 also seems to be sensitive to formaldehyde distributions, not as a cause, but as a diagnostic, as something that is concurrently changing in similar ways. And so this is something that we find very exciting. And with that, I feel like I've talked long enough. I want to come back to this picture from space and talk about how, we do want to develop better strategies for how to use the geostationary observations. We do want to talk about in the community about getting broader coverage for geostationary, or how to bring airborne to bear on other parts of the world. And so looking at this large part of the America Working Group domain that's important, and those 3 kids from Columbia at my table at IGAC who wanted to say, why can't we include Columbia? That's a conversation that I hope this talk can help us begin with this working group, in terms of, I don't know how long it will take, but I think it's thing that we need to be talking about. So thank you for listening. And I hope this is the beginning of many more conversations. Thank you.
Okay. Thank you very much, Jim, for a great talk. So many topics and very interesting.
Yeah, it's a lot. And I wanted to cover a lot. I didn't want to try to do one thing really, really well. I just wanted to throw a lot of ideas at you.
No, and that's right. I hope we already have a couple of questions in the chat, and
Okay.
so I can you can maybe answer them, and then we can open the Zoom meeting to more questions.
And I see Laura's question, and she's exactly right. Our modeler is making sense of the NO2 surface, the NO2 column. The person who told me it didn't make sense, that was 10 years ago, and they really were having trouble. They are getting better, but they're getting better in the average. I wouldn't say that they're doing great in the day-to-day. And that goes back to this question of, boundary layer parameterizations may be sufficient for the average, but are we really capturing the day-to-day variability in what's happening? And there's some great examples that I didn't show from Seoul, Korea, where we can see, just even in ozone titration, evidence that the boundary layer, especially nocturnal boundary layer, which is a real problem in big cities, is behaving in ways that the models do not capture. And so that really is, I think, an area for work to be done in terms of coupling meteorology with chemistry, and how NO2 distributions will change the nonlinear outcomes of chemistry from day to day in a domain. I see one from Rodrigo. How do you plan to integrate the Milagro results into the new campaign? So the Milagro results have already started into the conversations of timing, right? When should we come? And I think overall with Milagro is very, because how often do you get to go back to the same place at the same time of year? In this case, almost 20 years later, right? How different does it look? And if you look at the timeline from Mexico City, from Milagro until I would say the early 2010s, there was some real progress in air quality in Mexico City. But like many places in the US, that progress seems to have plateaued. And so this question becomes, what are the remaining things that we can do? Because the early things that you do to fix air quality are the easy things. But as you continue to try to push things down, it gets harder and harder. And that's a big question, I think, across the whole tempo domain, is as we try to move towards better conditions, where's the room left to make those changes? So Milagro will be an anchor, I think, an anchor point for hammock when we do the work in 2028. I will also tell this group that Michelle Gruder and I are committed to having an annual session at RAUGM. So at the end of October, the Mexican geosciences community meets kind of like their AGU, and we plan to have a session on this campaign that helps us plan. I hate that 2028 is so far away, but I'm also grateful that it's far away so that we can plan better connections, maybe a more detailed ground presence during the campaign, and make those scientific connections so that people like Rodrigo and Michelle and others can partake of and participate in the campaign. Right now, going back to that 777, there's interest in putting instruments on the plane. So it's so big that the risk is very small. We know we can do our science, but if Mexico or other countries have ideas for things that they would like to try to measure, we can do that. There's also so much room on that plane that we can take guests. And so if just having students or faculty or people come and be with us for a time, fly on the plane, watch data be collected is a wide open opportunity. So I think there's a lot of developmental opportunities that are opened up by a plane that's so much larger than the payload. We can bring guests. In Asia AQ, we flew, I would say, probably between 40 to 50 guest flyers. They're from the press. They do documentaries. They're students. They're from the environmental agencies. That's something we've been very good at, and I think we can do even better with the campaign. So getting to you now sets the stage for us to hopefully plan for a great interaction down the road.
Thank you.
I say this toward the end too, and this is sincere. For me to see that Mexico has a president who is a climate scientist who understands us is a stark contrast to what we have chosen to lead our country. And so I'm very, very encouraged by what I think is an opportunity in Mexico that can be an example for everyone, not just Mexico.
Thank you, Jan.
And I know you reported that, but so be it. It's my honest opinion.
There is a question from Olmo Zavala.
Oh, let me see.
I
need to scroll down more on that.
This is almost Zavala from Florida State University. Yeah, I'm participating with the Mexican government and the UNAM to try to improve their pollution forecast. I'm glad that you are already in communication with Michelle Gruder.
Yeah.
And it would be great to see you at the Mexican EU for sure. Sorry, I just got distracted a little bit. So when are the deployments happening in Mexico City?
The Mexico City deployments, we're looking at a period between April and May of 2028.
28. Yeah, it would be great to be in touch just to try to organize. I mean, because this project right now happening tries to improve the forecast with numerical models, but also with machine learning. So it would be great to see how the current data can communicate with those models. Mm-hmm.
I'm aware of work that Arthur Mitzi is doing with UNAM and others about this idea of creating that I think it's a DART system. It's a highly assimilated system. And while I'm not involved in that, I truly believe that everything we do is for the benefit of the models. And so if we're not feeding the models or testing the models, we're missing the point of the work. And so I'm glad to hear that there's going to be a lot of interest and attention paid to that.
Definitely. Thank you.
Laura asks, to what extent could we replace geostationary satellites by a network of Pandoras? I think that the Pandoras might actually be better at giving you what's happening diurnally. And so in an urban area, there's a whole nother talk I can do on that. I wish I had time for it. We find that diurnal trends are very well characterized by Pandora. And from the satellite, let's look at it this way. When you do a Pandora, you look directly at the sun. Every photon that is coming to the instrument, you know its path. And so the retrieval is much simpler. From space, you have optimal estimation. It's scattered sunlight. And so you have to make profile assumptions to make the retrieval. And so that makes the Pandora very useful. But the Pandora, again, can only be at very specific locations. So that's the shortcoming. They're better in a complementary sense. And in all honesty, Pandoras are still a research instrument. They still have issues, and we're still learning how they behave. But over my I could give you a Pandora talk sometime. I still think they have very, very valuable information to convey, and we have made great use of them. And so while we wait for geostationary and other places, I do think Pandora is a great tool to begin to understand the diurnal emissions and things that are going on in these large cities.
There is a question from Andres Jarce Botero.
Where did I skip over that one?
Hello, can you hear me?
Yes, I hear you.
Hello, James. Thank you a lot for your amazing presentation. I was wondering, in South America, sometimes also the computation capabilities are a problem. So what do you think about the perspective of emission estimation using lightweight methods? For example, this Gauss-Plum integrate mass enhancement cross-sectional flux method, this variety that don't are using models, and in which, in this perspective of airborne measurements, could be interesting also to think on that hybrid in South America.
Yes, and again, I only have so much expertise, and so I appreciate the question about how these different methods can be used. This is why I think getting this type of activity in so many places is important, because it's a different way to look at things. And so to me, being able to understand whether a model is distributing things vertically appropriately is fundamental to an emissions question, right? Because if you only have ground information, you can see changes that are happening due to emissions, but are also disconnected from emissions. They're dynamical in nature. And so we need, and this is where the question about can we use Pandora's, I think Pandora's next to ground measurements are a great way to get an idea of when the dynamical is dominating and when the emission and chemical is dominating. And so I'm more geared towards the information that can test your methods. I don't think we replace your methods. We simply provided a framework to test them and see if they're working well.
I have a question, Jim. One of the objectives of this work is to compare all this satellite data with ground data, and there are differences because they are measuring different things. And one of the things is try to validate all the satellite data, right? And see how it does. So my question is, do you see differences when you compare ground and satellite data in different environments, like even in Asia, where you went to different cities that I'm sure they have different emissions and different meteorological conditions, and the US or even Mexico?
I'm going to verbalize this for you very quickly.
Okay.
Because it's a whole nother talk. But for instance, in many places in the United States, the Pandora shows no diurnal trend in NO2. It's very interesting. But when you fly the plane, you see that the dilution at the surface is still happening. And so in some places, the mixing is fast enough to, or I should say, the photochemical lifetime and the mixing are in synchronicity, which means that even though you're emitting NO2, you're losing it fast enough so that the diurnal trend in the column isn't there. There are other places where we see accumulation. And so those are places where you don't have a short enough lifetime. So in Korea, the emissions are so large, you see an increase in the column throughout the day. There are other places where we see a decrease in the column throughout the day. And so while we often see higher NO2 on the ground in the morning, almost everywhere, what you see from space diurnally actually is quite variable. And so seeing it in one place is not sufficient to say what will happen in another place. And this goes back to this question of why to put Pandoras in many places, because you don't know until you look about the diurnal. It can be quite different.
So my question is this: so you cannot interpret the satellite data without taking into account all the environment where you are measuring, right? And what I want to know is the algorithm that you use to process all the satellite data. Do it have to change if you go to Asia or to the US, or now if you go to Latin America, would that change?
I'm going to be careful about this.
Or not? Sorry?
I'm going to be careful about this. So I know that the GEM satellite has struggled more than the Tempo satellite with their retrieval.
Okay.
And that may have something to do with the quality of models in representing North America versus versus Asia. And so yes, I do think that the retrievals. So if I put a different, when OMI flies over, when Trope OMI flies over, they only have to know what the atmosphere looks like at 1 p.m. And we have found over time that retrievals at 1 are much better than retrievals at other times of day because we've learned so much more about that time of day.
Okay.
But the retrieval actually has to have a different a priori for 8 a.m., 9 a.m., 10 a.m., and those a prioris aren't as good. And so we're working very hard to create the framework to do better retrievals with time of day. And so the radiation that we receive back at the satellite truly carries content on that, but the way that you do the retrieval is very sensitive. And so it's as big of a science problem as the campaigns, right? Yeah, it's very, very, very important.
Exactly, and especially if we're trying to get global data for all these global models and that, but you don't have a way to compare in other areas where there is not a lot of ground data, and I think that's an issue, right?
And many of these satellites rely on global models for their a priori, and the idea of more higher quality regional modeling in all of these places is really important to emphasize. Yeah. Right. So that we can look at the details. I like that idea.
So I'm wondering if there is any other question. Oh, yeah, there is one from Nestor.
Let me go down.
Yeah.
So the quick answer is yes. The political environment is so uncertain. I don't know what to think about that, but I also don't know how to stop. So I have continued to act as if everything will be fine. That we're in 2028 is actually helpful because it gives time for some of this to kind of work its way out. So I remain optimistic and I remain committed to the planning of these things. And so I think that in terms of the South American campaign, that we just need to continue looking at what we're planning for Mexico and how that might have to change for an area that doesn't have a geostationary satellite. Whether we start small with some Pandoras to do a little characterization of things like Laura recommended, or whether we go right out of the gate and ask for flights. My experience is that once you get a plane outfitted, it's easier to add things. And so while I think 2028 is a low probability for getting beyond Mexico, we shouldn't just say no to that. So let's spend some time thinking about what kinds of activities could be done in other places and whether we can support that. I'm always open. That's important. If we don't ask for things, we won't get things, right? So we have to be greedy.
Okay. Is there any other question? I think
I'm looking to see. I don't think there are.
I don't think
but,
so.
But we scratched the surface today. There's a lot more depth to all of this, but I really appreciate the chance to spill it all out to you and think about it. And if folks can go to Mexico for that meeting, that's another place to see each other face to face. Online is good, but face to face is better. And so think about that.
So, well, thank you very much, Jim, for this great talk. And thank you, everybody, for being here. And there will be our second seminar in the series will be in May. So you will be getting an invitation very soon. So thank you very much.
Okay.
Bye.
So it's good to see everybody. I'll see you at IGAC. Right?
Okay.
Bye.
Excellent.
Bye.
Okay.
Bye-bye. Thank you very much.
Yes.
Excellent.
Thank you.